Do you also think it's a bit sad that unless you work at a big research lab, AI is turning more and more into simply crafting a ChatGPT prompt? That's why I'm going back to the basics, back to a time when training a neural network meant implementing your own backpropagation. So the goal of this series is to implement a PyTorch-inspired deep learning framework from scratch in C++. In the last video, we implemented a neural network in PyTorch and trained it on the MNIST and FashionMNIST datasets. The PyTorch notebook of the last video is also a very good starting point as it contains all the functionality that we wish to support with our small deep learning C++ framework. Today we are going to start by implementing the Tensor class, which is the building block of all our neural networks. You might have guessed its importance from the fact that it's literally in the name of my not so preferred deep learning library, and even PyTorch, the library written by and for gods, is described as a tensor computing framework. First, let's go to Wikipedia and try to learn a bit about what a tensor is. Wikipedia can indeed be very scary unless you already have a lot of background knowledge on the topic, but as luckily is often the case, mathematics is just some fancy definitions to point to some intuitive concepts. Well, a tensor is just an object that can store some numbers, for example the weights of our neural network, and can be used in operations such as addition and multiplication, which also allow us to create new tensors. As I said, a tensor just needs to be able to store a list of numbers, and there are a lot of containers in C++, but as we just want to be able to randomly access elements using an index and also want to be flexible in how much data each tensor can hold, the vector is the obvious choice. We will also need to choose a data type for the numbers, and we will be using float as it uses 32 bits to store the float, and this is the same as the default that's being used by PyTorch. In C++, if you want to use a method or a class in multiple files, you will have to write that method definition in a separate header file. I don't think there exists a modern programming language where you also have to do this, so yeah, C++ sometimes feels very ancient. Nevertheless, in our tensor header file, let's declare 3 constructors for our tensors, as we initially want to only support scalar, one-dimensional and two-dimensional tensors. To store this data, we are going to declare a private data variable and also a shape variable to keep track of whether we are actually storing a scalar, a 1D or 2D tensor. For scalars and 1D tensors, the implementation is now very simple. A scalar has no shape, so we just initialize it as an empty list, and we just put our scalar in a vector and assign it to data. In the one-dimensional case, the shape is equal to the size of our data, and we can once again assign the data. But what about the 2D case? As our private data variable is a one-dimensional vector, we can just assign the data directly. So do we simply create another member variable for the 2D case? Well, no, as this isn't very scalable, as you can see. So what libraries like PyTorch and NumPy do is just flatten the multidimensional inputs to a single dimension. There are 2 main methods to do this. First off, the row major order method, where all the elements of the same row are stored together after one another. So all the elements of the first row are stored first, then all the elements of the second row, and so on. In a more generalized way, you could say that we are first storing the elements of the last dimension, then the elements of the second last dimension, and so on. The alternative is column major order, where all the elements of the same column are stored together after one another. So all the elements of the first column are stored first, then the elements of the second column, and so on. When you also generalize this to more dimensions, we are basically storing the elements of the first dimension first, then the elements of the second dimension, and so on. So anyways, as PyTorch stores its tensors in row major format, we are also going to do it like that. There isn't an optimal choice between row or column major. The only thing that's important is that you try to access the data in the same order that it's stored in your memory. That's because when your program wants to access an element of, for example, your vector, the CPU doesn't only fetch that specific value, but also fetches the next and previous value stored next to it in memory and loads them into your cache. So with the next read, your CPU will first check if the value can be found in the cache, which is much faster than having to access your RAM memory. So let's implement this row major serialization. To do this, we will add a new private member variable called stride. I will explain why we need this very soon. It will just help us with accessing the data. But now in the 2D case, we are first going to check if the row has the same amount of columns so that we know it's a valid matrix. And after that, we are simply going to store our data in row major order, which is very simple as we just need to store each row after one another. We are going to implement an item method, which in the case of a scalar or one-dimensional tensor with only one element, will just return a reference to that stored element. This is exactly how it works in PyTorch, where you also can't index into scalar tensors, but have to call this item method instead. Let's define the headers. For each of our access methods, we are going to provide a read-only variant, which returns a constant, and a write variant, which also allows us to modify the values that are stored in the tensor. Our implementation is also very simple. We just need to check if we are only storing a single element in our data member variable. If that's the case, we just return a reference, and if not, we throw an error. In the one or multidimensional tensor case, you can also use these square brackets to access elements in PyTorch. But as C++ only supports overloading the square brackets operator with a single index, and we also need support for multidimensional indexing, we are instead going to overload the call operator. Let's make some headers for both the one and two-dimensional accessors. In our one-dimensional case, the implementation is very straightforward. We first check if the tensor indeed only has a single dimension, and if not, we raise an error. In the one-dimensional case, we also check that we are not accessing any out-of-bounds data, because that's also possible with C++, and if this is not the case, we just return the data. For the two-dimensional implementation, we will have to map this row index I and column index j into an index for our linear representation. And that's also why we are storing this stride, as it represents how many elements you have to move to get to the next element in a specific dimension. In this example, as we are flattening a 3x4 matrix, the stride is 4, 1. This means that when the row index increases by 1, the corresponding element is stored 4 elements further, because there are 4 columns in each row. And as each row is stored after one another, the stride for the column dimension j is simply 1. This provides us with a very easy formula to convert a 2D index to a one-dimensional index. Note that we understand the formula. The implementation is very straightforward, as we once again first check that we are indexing into a two-dimensional tensor and check we are not doing anything out of bounds. Then we just convert the 2D indices into a single index, which we can use for our linear representation using our stride. And it's as easy as that. Let's now verify that we can indeed construct a tensor. But to verify this, we will have to implement our own custom printing method to visualize the data. Of course, in Python this is very easy, as the print method of a list is already implemented for us, but this is C++, so let's quickly override the stream insertion operator to first build a string of the tensor and then output the string to the terminal. We will also have to implement some methods to view the shape and stride of our tensor for this to work. Let's now construct a one-dimensional tensor and print it. It seems to be working. Let's also quickly create a two-dimensional tensor, and also this seems to be correctly constructed. However, just eyeballing things might not be the best way to verify if I implemented everything correctly. Luckily, like almost every programmer, my favorite part of software engineering is writing unit tests. So let's get started. We will quickly implement a test which initializes some tensors with some dummy values and then tries to access those values through the access methods that we have written. I will also check some edge cases to see if we can't access elements that are out of bounds. And indeed, after running the test, our implementation seems correct. As I said, tensors just store some data and provide some operations to create new tensors. We have now implemented the data storage part and are just going to define the only two operations required to train our neural network. We will first start with the element-wise addition. Let's first define the header of this method. For this, we will be overriding the plus operator of C++. I will also be using shared pointers. A shared pointer, by the way, is called a smart pointer and is indeed very smart, as it will automatically manage the memory for us. When you declare that an object is of the type shared pointer, it will be allocated on the heap, and the shared pointer will store the memory address of the object together with how many other shared pointers have a reference to this object. And once the last shared pointer is destroyed, the object will be automatically deleted, which is of course very useful to prevent memory leaks. Right now it might not be obvious why we want to allocate these tensors on the heap, but here's a quick spoiler warning, so if you don't want any spoilers, just skip ahead for a bit. But to implement automatic differentiation, we are going to build a computation graph. And what this means is that each tensor will need to store pointers to the tensors that were used to create it, and to make sure that these pointers stay valid after the function that created them ends, we have to allocate these tensors on the heap. Also in neural networks, the same tensor can potentially be used in multiple operations, so we need to make sure that the tensor memory is only freed after all the objects pointing to it are destroyed. Note that we understand the C++ technical details. Let's have a closer look at what the addition operation actually means in the context of tensors. Let's go over them case by case. When we're adding a scalar to a one-dimensional tensor, the resulting tensor is created by adding the scalar to each element of the one-dimensional tensor. If we add a scalar to a two-dimensional tensor, this is exactly the same. For the addition operation, it also doesn't matter if the scalar is to the left of the tensor or to the right, the result is just the same. When we're adding a one-dimensional tensor to a one-dimensional tensor, we create a new tensor by taking the same element at each position in both tensors and adding them. This also means it's important that the dimensions of both tensors match. The 2D case is once again straightforward. Make sure that the dimensions match of both tensors and then just sum the elements that have the same row and column index. Let's also go through the implementation case by case. When we're adding two scalars, we first take the sum of both scalars. And for those of you without C++ experience, the arrow symbol right here isn't an emoji to make the code more fun, but instead allows you to access the values that the other tensor, which is passed as a pointer, is storing. We then use this sum to create a new tensor, which we allocate to the heap and return a shared pointer to. In the case of adding a scalar to a one-dimensional tensor, we have seen that we should just add this scalar to each element of the one-dimensional tensor, so we create a vector to store the result of adding the scalar to each element of the 1D tensor. Once again, for clarity, just like the arrow operator, adding a star in front of a pointer also allows you to dereference it, but in this case, as we are using our accessor methods, which are done with these parentheses, I think it's a bit clearer when you use the star to dereference it. We then create a new operator, a new tensor with the result, create a shared pointer to it and return that. The case of adding a scalar to a 2D tensor is just the same. but this time the result is also a 2D tensor. So we once again loop through each element of the 2D tensor and store the resulting sum in the 2D vector, which we will then use to create the resulting tensor. We are also going to support having the one-dimensional tensor at the left side of the plus operator instead of the scalar, but this is almost exactly the same as we have implemented before. Same for having the two-dimensional tensor at the left side. Now there are only two cases left. First off, the one-dimensional tensor plus one-dimensional tensor, for which we should check that the dimensions of both tensors are equal, or else raise an error. Just like before, just create a vector to store the result and add the values at the same index in both vectors. Then just use this result to create a new tensor. Finally, the two-dimensional plus two-dimensional case, we have already checked that the first dimension is equal, but we still need to check that the second dimension is also equal of both matrices. Then we are once again going to iterate over all row and column indices and add corresponding values. Finally, return the result as a shared pointer to a tensor. Let's now quickly implement a test to check if what we implemented is correct. As always, this is the most fun part and you should definitely not use AI to generate these test cases. Indeed, our implementation was correct. Clearly, I am the reincarnation of Terry Davis. Okay, and now at last, we have finally reached arguably the most important operator in all of deep learning, and that's the multiplication of tensors. Let's get started right away. The function signature of matrix multiplication will be as follows. This time we are overriding the star operator. This might be a bit confusing as this operator is used for element-wise multiplication in PyTorch and matrix multiplication is actually done with the odd operator, but as C++ doesn't have this odd operator, yeah, we are just going to overload the star. But anyways, just like addition, we are once again using shared pointers for the same reason as I already explained. Let's start with the easiest case, multiplying two one-dimensional tensors. Both tensors should once again have the same shape, and what we are going to do is multiply the elements of the same positions and sum them. Very easy, right? So the output of this is a tensor with a single element. Next up, multiplying a one-dimensional with a two-dimensional tensor. In this case, it's important to realize that the one-dimensional tensor should have the same amount of elements as there are rows in the two-dimensional tensor, as we are going to multiply the one-dimensional tensor with each column of the two-dimensional tensor, just like we did in the 1D times 1D case. So once again, very easy. Now for the two-dimensional times one-dimensional tensor, we are going to do something similar and just taking all the rows of the two-dimensional tensor and multiplying it with the one-dimensional tensor. So in general, what's happening in all of these cases is that we multiply each row on the left-hand tensor with each column of the right-hand tensor. And just like in PyTorch, a one-dimensional tensor on the left side should just be interpreted as a row, and a one-dimensional tensor on the right side should be interpreted as a column. So this is also how you should do the matrix multiplication of a two-dimensional times two-dimensional tensor. The resulting tensor has the same amount of rows as the left-hand tensor and the same amount of columns as the right-hand one. Note that we have hopefully gained some visual understanding. Let's try to implement all of these cases in C++. Matrix multiplication is not defined for scalar tensors, so let's just add a check for that. As I also explained, we also have to check that the last dimension of the first tensor is equal to the first dimension of the second tensor. In the case of one-dimensional tensors, this just resolves to having the same amount of elements. For the one-dimensional times one-dimensional case, the result of matrix multiplication is a float, so let's keep track of that. Then we are just going to iterate over both tensors, multiply the elements at corresponding positions, and add them to the result accumulator. We are then just going to create a new tensor with this result and return it. In the 2D times 1D tensor case, the result is a one-dimensional tensor, so we create a vector to keep track of the result. We are then going to iterate over each row of the two-dimensional tensor, and for that specific row create a variable in which we are going to accumulate the result from multiplying each element of that row with the corresponding element on the same position in the other one-dimensional tensor. Finally, we push this element to the result vector and then once again create a tensor out of it. The result of the 1D times 2D tensor case is once again a one-dimensional tensor, so let's just create a one-dimensional vector to keep track of the result. What we now need to do is iterate over each column of the two-dimensional tensor and create an accumulator in which we can store the result of multiplying each element of that column with the corresponding element in the one-dimensional tensor. Then we once again push this accumulator to the result vector and create a tensor with that result. Finally, the two-dimensional case. This time the result is a two-dimensional vector, a two-dimensional tensor I mean, so let's create a two-dimensional vector. It's a bit more complicated in this case as we will need 3 for loops, but what we are going to do is iterate over each row of the left-hand 2D tensor, and then for each row consider this basically as the one-dimensional times two-dimensional tensor case from before, which just means that the result of this is also a one-dimensional tensor. Thus, we once again create a vector to store this result. Now we can just multiply the one-dimensional tensor with each column of the two-dimensional tensor by having a third loop, which will allow us to index into and multiply the corresponding elements of the ith row with the jth column. And the result write it to an accumulator, and then once again add this accumulator to the result vector for the ith row. And once we have calculated this for all the rows of the left-hand matrix, we can then just add this vector to the final result vector. We can then use this result vector to create a tensor of the result and return that. If something is not clear, which I definitely understand, I would just pause the video and manually trace this algorithm, because it might be a bit hard to follow from just looking at the code. As always, let's implement some quick test cases to check if the matrix multiplication is actually working. Run it, and it seems like we made a mistake. Oh no. After going through all the matrix multiplication cases again, I noticed I made a mistake in the 1D times 2D case. If you were paying close attention, you might have spotted this. I'm sorry, I will take back that I'm a godlike programmer like Terry. Let's just quickly fix the test, and okay, everything seems to be working now. Congratulations, you have reached the end of this episode, and if you understood everything, you now already have an in-depth understanding of a very important aspect of deep learning. However, as you might have guessed, there is still a long road ahead, and in the next video we will be looking at implementing our own backpropagation for the tensor class and how we can build a computation graph. The next episode will probably be the hardest episode of this series, but at the same time also the most rewarding and probably the most interesting part of the entire implementation. So if you truly want to understand how deep learning works and you find this interesting, I would recommend you to subscribe to my channel. Anyways, I hope you enjoyed this video. Leave a comment down below if you liked it or have some feedback. Anyways, I hope I see you in the next one.